Okay, so we are going to use rectangles to approximate the area under the curve. And this comes in two parts. So the first part is we're going to find a very rough approximation using right and left endpoints, and we'll have a fixed number of rectangles. So just to be honest, I'm only going to do right because it is what we're going to use in the second part, which is where we're going to find the exact area using summation, remember with our sigma, and formulas, right, the summation formulas we had, and limits. Okay, so in general, this is what we're doing. We are going to approximate the area between a function and the x-axis. So in this case, between x equals a and x equals b, we want to get an approximation for this area here. And what we're going to do is use rectangles. So as you can see, we have some choices to make. Would we want to draw our rectangles? And you can see I have it divided here. I have 3 little hash marks, so I'm going to do 4 rectangles. And so the area of a rectangle is its width times its height. Well, which height are we going to use? So for instance, if we look here at the third rectangle, would we use this left endpoint or the right endpoint to give the height? Well, as I just said, we're only going to use the right. So there's our key. Okay, so we have 1, 2, 3, 4 rectangles. And we want to know what these x values are because those are going to give us the heights of our rectangles. Okay, so n stands for the number of rectangles. The width of each rectangle is delta x, and delta x is equal to b minus a, right? So the total distance of x's that we have to cover, divided by n, where again, n is the number of rectangles. So in this case right here, n is 4. Now, what we do, so a, I always call x sub 0. It's our first x value. This next one is x sub 1, and that is equal to a plus delta x, right? It's one step across. X sub 2, right? That's going to be a plus 2 delta x's, and so forth. So now let's talk about what the area is going to look like, what that formula will be for us. So our area approximation, so we're going to add up the area of each rectangle, right? So the area of that first rectangle, right, is its height, which is f evaluated at x sub 1, but right, we need x to take on, right, we need x sub 1, x sub 2, x sub 3, x sub 4. So we'll do x sub j, we'll make it generic, and then we'll let j go from 1 to 4. Okay, so here are the heights of each of the rectangles, and then we are going to multiply the heights times delta x. So that's going to be, right, x sub 1, f of x sub 1 times delta x, plus f of x sub 2 times delta x, plus f of x sub 3 times delta x, plus f of x sub 4 times delta x. And yes, x sub 4, that last one, x sub n, also equal to b. All right, so that's in general what we're doing. And yes, I know some of you, if you draw in all of those rectangles, so you're going to see we are definitely going to be overestimating the actual area. If we would have taken the right endpoint, or I'm sorry, the left endpoints, we would be underestimating. So I want you to keep that in mind when we get to part 2, where we're going to find the exact area using the limits. Okay, so let's do an example. So we're going to find r sub 4, so r for the right endpoint. That's what the r stands for. 4, this is the number of rectangles. And we have our function, so negative x squared plus 9, and we're going from negative 2 to 2. So we'll start with a sketch of f of x. So it's an upside down parabola, raised up 9. And we're going, so it crosses at negative 3 and positive 3, right, for its x-intercepts, but we're going from negative 2 to 2. So first off, how big is our delta x? So formula for delta x, remember, so delta x equals b minus a over n, so 2 minus negative 2 over 4. So delta x equals 4 over 4. So that's 1. Yes, I did make it nice on us. It does not have to be an integer. Typically, it's nice-ish, though. So 1, 1/2, something like that. So let's think of what our x sub i's are, right? So x sub 0, also known as a, is equal to -2. X sub 1, right, is a plus 1 delta x. So that's -2 plus 1, -1. X sub 2, right, a plus 2 delta x's, or you can just add your delta x to your last x sub 1, right? So -1 plus 1, x sub 2 will be 0, x sub 3 will be 1, and x sub 4 will be 2. So now we're going to find the function values, add them up, and remember, we're doing area of rectangle, so it's the heights times the widths. So let's see, my x's are -2, a -1, a 0, a 1, and a 2, and the right endpoints I'm just going to go up and draw those rectangles in. So there are my 4 rectangles. So that first rectangle, its height is f of -1, and then times its width, delta x, which is 1. And my second rectangle, f of 0, is its height, right? So now this guy right here, its height is f of 0, and then times its width, also 1. F of 1 times 1, and then finally f of 2 times 1. So let's find those values. So f of -1, remember f of x, let's put that in here just in case I need to move. I'm going to switch my order around a little bit. So 9 minus x squared. So 9 minus -1 squared. Thanks, Piper. 9 minus 1 is 8. So I have 8 times 1 plus f of 0, that's 9 times 1, plus f of 1, that's another 8 times 1, plus f of 2, let's see, that's 4. 9 minus 4 is 5 times 1. So I don't know if you noticed here or not, and it was kind of hard because they were 1s, and 1 isn't all that exciting because it doesn't change the value. But those were delta x's, and they're the same in each of them, so we could have factored that out, especially if it was a fraction or something ugly, moved it to the front, and then done that multiplying later. But for us right now, it's 8 plus 9 plus 8 plus 5, what is that, 16 plus 14, so 30. 30 is our approximate area. All right, so now we're going to take that, and we're going to use it to find an exact area by letting the number of rectangles go to infinity. Okay, so as we saw, so I didn't say it out loud, but those r sub n's, right? So to get the sum of the area of the rectangles, so n rectangles using the right endpoints, so the delta x factored out front, and then we do our function evaluated from I equals 1 to n. Okay, we just did that with n equals 4 and delta x equals 1. So here we go. We are going to do a similar example. So we have f of x equals x squared plus 4, and it's going from -1 to 2. So same steps. Let's determine delta x. So delta x, b minus a over n. But we're going to keep n the variable because we're going to let it go to infinity, right? So b minus a over n. So 3 over n is our delta x. So then determine your x sub j's or x sub i's, whatever your counter is going to be. So, right, x naught is a, which is -1. X sub 1 is -1 plus 1 delta x. X sub 2 is -1 plus 2 delta x's, right? Or in general, right now that we kind of see the pattern, x sub j would be negative 1 plus j times delta x. Okay. So now here we go. Look up top. We need to find r sub n by doing delta x times the sum of the function evaluated at x sub j. Okay, so f of x sub j equals, so here's my f of x. So I have, we're giving it x sub j. We're giving our function all of that. So it's negative 1 plus j, how about 3j over n squared plus 4. So we'll do that algebra. Okay, so that equals, let's see, 1 minus 6j over n plus 9j squared over n squared plus 4. So altogether, f of x sub j, so I'm just getting that right-hand side. So 5 minus 6j over n plus 9j squared over n. So there's my f of x sub j's. Now let's write r sub n. R sub n equals delta x, 3 over n, times the sum, j goes from 1 to n, of f of x sub j. I'm just popping that over. Now we know from some of our summation rules that we can go term by term, and if we have constant multiples, they can move in front of the sum. So this is what we're really going to do, right? So we have 3 over n times, we'll do the sum of 5, j1 to n, minus 6 over n times the sum of j from 1 to n, plus 9 over n, oh, that was supposed to be n squared of j squared, as j goes from 1 to n. Okay? All right, and we have formulas that I wrote down on a little sticky note for those summations. So we can do, right, these summations using our formula. If we, oh, I don't have the constant on there. You add up a constant n times, that's just 5 times n. All right? Okay, so we're going to put all of that together, right? Get those formulas copied down if you don't have them already. Keep a sticky note handy or a flashcard if you have it. I'll keep mine right there, so I've got some room. So r sub n. So we have 3 over n times, I have 5n for my first sum, minus 6 over n, looks like I've gone to capital N, sorry about that. And then the sum of j's from 1 to n equals n squared over 2 plus n over 2. So n squared over 2 plus n over 2. And then plus 9 over n squared times the sum of the j squareds equals n cubed over 3 plus n squared over 2 plus n over 6. Okay, so here is our r sub n, all multiplied out and summed up. So let's go ahead and tidy that as much as we can, and then we'll do the limit. So 3 over n, I have 5n minus, so I'm going to distribute, so I'll have 6n over 2, so how about 3n for the first one, and then minus 3, right, when that distributes, check my algebra, and then we'll distribute the 9 over n squared, so I'll have 3 plus 3n plus 9 halves plus 3 over 2n Okay, keep going with the algebra. So what do we have here? Minus 3n plus 3n. Those guys will go away. So it looks like I have a 5n. I'm just keeping track here. Plus 3 over 2n. Saving my math for the last. So then I have 9/2 minus 3. So what's that? 4.5 minus 3. So 1.5. So plus 1.5. Okay, last thing, we'll distribute that 3 over n. So we get r over n equals 15 plus 9 over 2n squared plus 9 over 2n. Oh my gosh, thank goodness we're done with the algebra part. Let's get back to calculus. Okay, so what we want to do is take the limit, and I'll get some blue for calculus here. We're going to take the limit of r of n as n goes to infinity. So I have the limit of 15 plus 9 over 2n squared plus 9 over 2n as n goes to infinity. So limit of a constant stays a constant. And when we have that n in the bottom, right, I have 9 over something really big plus 9 over something really big. Those all go to 0. So my answer is 15. So there's a lot of messy algebra. Having the summation formulas handy is very helpful. And the good news is we learn a much quicker way very soon.